Today we're looking at animating a 3D spinning top from scratch in Python using the laws of physics. What this means is taking Lagrange's equations for a spinning top, solving them in Python, and plotting the solution. And so I'm pretty good at doing this sort of thing in Python. I can solve systems of equations, I can get solutions, but I'm not an expert in animation. So what I did is I reached out to people on my Discord server, there's a link below to that, and I said, hey, could someone please help me make a beautiful animation of a 3D spinning top? And someone named Amzal from U of T reached out to me and said, hey, I can do it. And he, in a very few lines of code in Matlab, was able to animate the spinning top. I'll let Amzal briefly introduce himself, as he was a huge help to this video.
Hey guys, my name is Amzal, and I'm part of the Spacecraft Dynamics and Control Laboratory at the University of Toronto. My research work mainly focuses on solar sail vibration and attitude control.
Please be sure to like and subscribe if you enjoy this video. There'll be tons of stuff like this in the future. I'm really looking forward to collaborating with people as well. So join the Discord server and enjoy.
Throw down my spinning top. I got a notion that Lagrange's equations will govern the motion. Too long for pencils, that's for simple as my guy. Got equations on the fly, easy as pie. Look at these beauty animations that I got, y'all. 3 cheers for Amzal, Matlab essential. Hope your heads are spinning, cause we about to be beginning. Let's solve some equations, yeah, we be winning.
So I've put some useful links here for understanding all the material. These are specifically for understanding things like the Euler angles, which are a little bit complicated, and I don't want to get into too much depth in this video, and defining the angular momentum, for example. And so packages today are pretty standard. We have NumPy, always used in this sort of stuff. Matplotlib for a little bit of plotting. SymPy is used for all the symbolic manipulation, because of course we need to derive Lagrange's equations before we solve them. Once we have Lagrange's equations, then we need to numerically solve them. That's what SciPy here is for. And then we'll do a little bit of plotting with Plotly, for example. And afterwards, of course, we'll create a beautiful 3D animation, which of course you've already seen. So I can import all the packages here. And so for solving Lagrange's equations, of course, we need to define specifically what our free variables are. For example, a mass on a spring, it might be the distance or the stretch length of the spring. That's the free variable. So you have one free variable. Now for a spinning top, where the point is fixed on the bottom, it turns out that you have 3 free variables. And the most convenient way to express these is in terms of the Euler angles, which you see here. So you have theta, you have phi, and you have psi. So imagine you have the spinning top here. Theta would be the tilt angle of the spinning top. Phi is the sort of rotation in the xy plane of how it's rotated once it's tilted. And then psi is the rotation of the spinning top. So you can think if you have a spinning top that's spinning really fast, it might have a really small theta tilt. And the derivative of psi with respect to time is moving really fast because it's spinning. And then it turns out that phi, it'll also revolve around as it spins as well. So you can show that the angular momentum vector in terms of the xyz plane is given by this. So this is phi, theta, and psi, the Euler angles. Now this is non-trivial, and I'd recommend looking at the links, for example, I provided at the beginning of the video to confirm this. But this is not an easy thing to necessarily derive, and I don't want to get into too much depth in this video about this. Now, once you have the moment of inertia tensor for the object, by the way, I went over that in my last video. There's a link in the description. I'm not going to be going over that as much in depth in this video, but I showed how to find the moment of inertia tensor for any object that you want. So it can be applied to this video as well. But once you have the moment of inertia tensor and you have the angular momentum vector, the kinetic energy is just 1/2 omega t I omega. Remember that I is a matrix and omega is a vector here. the potential energy, so you have the kinetic energy, then there's also the potential energy of the spinning top. And now if the point is fixed, the potential energy is the center of mass location above the ground. So if h, for example, is the z location of the center of mass, the potential is mgh cos theta, because as the spinning top tilts, the center of mass, of course, is moving down. So it's a pretty easy expression for the potential energy. So the Lagrangian looks actually pretty simple. It's L is t minus v is 1/2 omega t I omega minus mgh cos theta. Of course, this is a matrix equation here, but you get a scalar that comes out because I omega is a vector, and then it's sort of like a dot product between two vectors. So you get that. It looks simple, but of course it's quite complicated once you start getting into the math, and definitely not something you want to do by hand. So we have a Lagrangian, which means we can find Lagrange's equations and solve for the equations of motion with this. But of course, there's a lot of free variables here. There's m, of course, the length of the spinning top, for example, as well, comes into play with the moment of inertia I here. And so what I like to do is I like to make things as dimensionless as possible before solving the problem. So I let L, which is not the Lagrangian here, this is the length of the spinning top. Notice that this is a curly L. That will be the length of the spinning top from top to bottom, essentially. And m be the mass. And so we can divide everything by ml squared to get something that looks like this. So I have the Lagrangian divided by ml squared is 1/2 omega t I over ml squared. This is a really easy quantity to compute. For example, you'll note that I is always expressed, for example, a spinning sphere, I is equal to 2/5 mr squared. So there's always an mr squared factor. So it's convenient to divide by this factor here. You'll see that once I start getting into the code. And then I have a g over L factor and an h over L factor. So h over L is just the, if it's 0.5 h over L, it means that the center of mass is halfway up the spinning top. So this is another convenient quantity to express as well. And so what I'll do is, rather than dealing with this messy equation, I'm just going to prime everything that has this divided by factor. So L prime is 1/2 omega t I prime omega minus g prime h prime cos theta. This is an easier equation to deal with here. And in the code, I'll omit the primes, but just note that this is really the equation we're dealing with. And you might ask, well, can I use L prime as the Lagrangian like L? Do I get the same equations of motion? And yes, I do, because I can multiply the Lagrangian by any constant, which is ml squared, and I'll get the same equations of motion. So now we start getting into the code. We want to set up everything so that we can solve Lagrange's equation. We want to get equations that we can solve numerically. And to do that, we need to take a bunch of derivatives of Lagrange's equations and find the equations of motion. And this is a real pain to do by hand, but using the symbolic power of SymPy on the computer, this is very easy to do. So we start by defining all the appropriate symbols that we need for this problem. So I have t for time, h for the height of the center of mass, and g for gravity. I define them as t, h, g. And I also define theta, phi, and psi, the Euler angles. But I define them separately because I want to make sure I define them as functions. So for example, I define t, I have my variable t, I can go t squared, I can take functions, simp.sine of t, and I can do all sorts of symbolic manipulation there. For theta, right, I explicitly, after I define them, I say that theta is a function of time. Phi is a function of time, psi is a function of time. We don't know what those functions are, but we start by defining things that way. So if I look at theta, for example, it specifically says theta, which is a function of t. And same thing with phi and psi. And this allows me to define derivatives of these quantities, which I do below. So I say simp.diff theta of t, and I get ddt of theta. So again, I can keep track of things, and once I start plugging things into expressions, it will keep track of things like this. And I define the second derivatives as well. So underscore d just means one derivative, and underscore dd means the second derivative. So if I look at theta dd, it's the second derivative of theta. So the next thing I want to look at is the transformation matrix. And essentially that is, for a point in the green system, if I have a vector pointing somewhere, what does it look like in the red coordinate system? What is my vector expressed in that coordinate system? And you'll note that for the spinning top, by definition, the top of the spinning top is always along the x3 axis at 1, 0, 0. That's what the vector is. So how do I rotate in the red system as a function of these three angles? What does that vector look like? And so to go from the green system to the red system, I first rotate by phi, then by theta, and then by psi, like this. And the full rotation matrix is just the product of these three matrices. So I define these using the simp.matrix matrix, for example, and I plug in psi, theta, and phi. If I look at R3, for example, it's just a matrix with cos, psi, which is a function of t, and things like this. I have all three, and I multiply them. This is matrix multiplication, by the way. And if I want the position of the top of the spinning top as a function of time, I take my matrix R, which is the full rotation matrix, and I multiply by this z hat vector, right? 0, 0, 1, of course, is just pointing along the direction of x3. And so this tells me what the top of the spinning top is as a function of time. How does the top, move through the 3D coordinate system? And it looks like this. And so once I find theta, phi, and psi as functions of time, of course, it doesn't depend on psi because psi is just the rotation of the spinning top, but I can plot the rotation of the spinning top in the red coordinate system once I solve for these functions using Lagrange's equations. So next what I do is I define the angular momentum vector omega in terms of the Euler angles. Of course, I express this up here. I just write this down. The derivation for this is complicated, so I just define it like this. And so this is my vector omega expressed in terms of all three Euler angles. The next thing I do is I define the moment of inertia tensor. So all of these quantities, you'll note that there's 6 free variables in the moment of inertia tensor because it's a symmetric tensor. So I define some new symbols in SymPy, and then I define my moment of inertia matrix. Of course, this is all symbolic right now. So these are all the quantities here. Once I'm given a specific 3D object, I can load it into Python and I can obtain this tensor. And that's what I did in my last video. But we'll leave it just symbolic for now. Next thing, of course, we define the Lagrangian. So my kinetic energy is 1/2 times omega t. And I take the dot product with I times omega. That's just the expression up here, expressed in terms of a SymPy function. So that's what I'm doing here. My kinetic energy, I define my potential energy like I did above, and my L is T minus V. So for example, if I look at T, it looks simple when you write it in this form, but it's actually quite a long expression for the kinetic energy. And my Lagrangian turns out to be quite a long expression here. This is why I'm saying that it's probably not something that you want to do by hand. And of course, that's your Lagrangian and it's long, and now you have to find Lagrange's equations for 3 different variables. So you'll note that Lagrange's equations look like this. Now they're really equal to 0, of course, but we want to just obtain what this left-hand side looks like. So it's dl dx minus d dt dl dx dot. And that's for each of x's in theta, phi, and psi. So we have 3 free variables in this problem. There's going to be 3 Lagrange's equations. And so that's what I do. And so LE1, I differentiate the Lagrangian with respect to theta minus the derivative of L with respect to theta dot, and then a derivative of time outside that. So this is dl d theta dot. That's this expression here. And then the whole thing I differentiate with respect to time. So you'll see that there's quite a few derivatives, of course, that are going on here, and this would be a real pain to do by hand. And as you'll shortly see, these equations are very, very, very long, and not the kind of thing that you want to sit down and do with a pencil. So that took about 10-15 seconds to do on a computer. Usually computers can do this stuff really fast, and I think that really says how much of a pain it would be to differentiate the Lagrangian with all these variables. So for example, if I look at my first Lagrange's equation, everything that's equal to 0, I get something that looks like this. So this is not really the kind of thing you want to write by hand, because of course you'll miss a factor of 2, or you'll miss a factor of 2 here, or a factor of 4. It's a real pain, and the nice thing about the computer is you're guaranteed that this is correct. Now this is one of 3 equations, right? There's 3 equations total. And so, for example, this is the second Lagrange's equation, also a really, really long, annoying equation. And so what we're going to do now is we're going to find some differential equations that we can solve. So you'll note that all 3 of these equations are equal to 0 for each of capital X's and theta, phi, and psi, the 3 Euler angles. And what we want to do is we want to find theta dot dot, phi dot dot, and psi dot dot. And you'll note that all of these equations are linear in terms of second derivatives. You might have a factor of theta dot squared, you might have sine of theta dot, you might have all these things. But in terms of the second derivatives, these only ever show up in terms of linear factors. So we have 3 equations and 3 unknowns, and it's linear equations in terms of the 3 variables that we're looking for. So we can solve for theta dot dot, phi dot dot, and psi dot dot. Once we have these second derivative equations, we can solve these in Python. So I plug in all three of my Lagrange's equations up here. They're all equal to 0. And I look for theta dot dot, phi dot dot, and psi dot dot. In other words, I want an expression theta dot dot equals this, phi dot dot equals this, psi dot dot equals this. And so I'm going to solve for these. So SymPy can solve linear equations pretty simply. And so if I want the solution for theta dot dot, for example, I go sols, and I plug in theta dot dot, solves for solutions. And I can look at this, and this is a really long expression. So this is theta dot dot equals all of this. So a big fraction. Really something that you don't want to deal with by hand. I mean, good luck solving this differential equation. You have cosine of psi and theta, and there's 3 of them, and they're coupled, right? These are coupled second-order differential equations. But the beautiful thing about the computer is that you can solve it really quickly on the computer. And so I have one of these for theta, phi, and psi, and they're coupled second-order differential equations. So they can be written really concisely like this. Theta dot dot is one function of theta, phi, and psi, and the first derivatives. Same thing with phi dot dot and psi dot dot. And these can be solved on a computer really simply. Now, since Python doesn't deal with second-order ODEs, but rather first-order ODEs, we define some new quantities. We define Z1 as theta dot, Z2 is phi dot, and Z3 is psi dot. So now we have 6 variables. And this is just a trick to solving second-order differential equations on a computer. And we get 6 first-order ODEs. We get theta dot is Z1 by definition, and then Z1 dot, which is really theta dot dot, is equal to F1 of all these variables. So now we have 6 first-order differential equations that we can solve numerically using SciPy. So what we do is we convert these SymPy symbolic functions into typical Python numerical functions. So I want to be able to plug in a bunch of values here, a bunch of numbers, and get a number out. And so dz1 dt underscore f, because this is like a numerical function, I use SymPy's lambdify function. And so these are all the variables it takes in. Of course, it depends on gravity, center of mass, the moment of inertia tensor, theta, phi, and psi, like you see here, and Z1 and Z2 and Z3, which are the first derivatives. Remember, Z1 is theta dot. And so these are all the variables it takes in, and this is the thing that I want to lambdify itself. And I also do the same thing for d theta dt, but you'll note that d theta dt is just, Z1, so I'm just lambdifying the function and it returns itself, essentially. So these are really simple. It's these second-order differential equations that take in all the variables. And I do the same thing for phi and psi. And so, like I said, this becomes a numerical function. So I can take this function, and how many arguments does it take in? It takes in 1, 2, 3. It just takes in all these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Take in 14 arguments, and it will return a number. So now Python can use this to iterate through and solve the differential equations. So now we define our system of equations, and this is the typical way to do it in Python. You define a vector S, which is theta, Z1, phi, Z2, psi, Z3. We want to find the solution to all of these variables. So we have to define a function, ds dt, that takes in s and t, and it returns the derivative. So a function takes in s and t. You can see this function is taking in s and t, and it returns ds dt. So first I extract the things from the vector itself, and I return d theta dt, dz1 dt, d phi dt, dz2 dt, d psi dt, and dz3 dt, using these lambdify functions that I have above. And of course, this is what ds dt is. ds dt, of course, is d dt of theta, so d theta dt, dz1 dt, d phi dt. So this is an easy way of setting up the differential equation. So I define this function. And so now we need to obtain all the information about the spinning top. So I did this in my previous video. I loaded in a bunch of coordinates of the 3D spinning top, and I solved for the moment of inertia tensor. Of course, that's what we need in order to plug these into this function here. And if I know the shape of the object, I also have the z location of the center of mass, which is h. So I did this in the previous video. I'm not going to go through it a whole lot of depth here. But if you want to know what I'm doing in this cell, be sure to watch my previous video, link in the description to that. Now I define the mass of each voxel. You note that the spinning top has a bunch of different points, essentially, and I want to know what's the mass of each one of those points. Well, the first way is just say all of them have the same mass. All of them are equal to 1. So it's an isotropic spinning top. So m They're all equal to 1. So this is just an array of 1s that's equal to the length of the coordinates. So that makes it really easy. If I look at M as an array, it's just a bunch of 1s. That means that every voxel has the same mass. Then I compute the moment of inertia tensor. Again, this is done in my previous video. I'm not going to go through a whole lot of depth here about what I'm doing. And I define the appropriate quantities as well. So G prime is G over L. And gravity is 9.8 meters per second. So G over L, which is really what G is in the code, is 9.8 over 0.05. Remember, I'm dealing with G prime here. H is the location of the center of the mass. And I can do that by taking a weighted sum. Chords 2, of course, being the Z coordinates of the voxels. So this is a weighted sum to find the Z location of the center of mass. So, of course, when I'm solving a differential equation, I need to give the appropriate initial conditions. So I say that theta naught, which is the initial tilt of the spinning mass, is pi over 4. There's no tipping velocity, so it's not tipping, it's just 0 velocity when it starts. Theta, or phi naught is equal to 0. This is just arbitrary. Remember, phi is like the rotation like this. So phi equals 0 is just arbitrary, and phi naught dot is 10, so it's slightly kind of revolving around when it starts. Psi naught is equal to 0. This is the rotation of the spinning top as it's spinning really fast. So of course, psi naught equals 0 is arbitrary. It could be any angle, so I may as well set it equal to 0. But psi naught dot is equal to 120 pi, so that's a really large number. And that's because the spinning top is moving really fast when you let go of it, so it's spinning really fast. So I let go of it, it's got an initial theta naught angle, and it's sort of initially spinning like that. And the question is, what is the motion of the spinning top? So now I solve the differential equation, and I'm going to solve it between t equals 0 to t equals 2 seconds. So that's my array here, 10,000 points between 0 and 2. And I use SciPy's ODE int function to solve my differential equation. I plug in ds dt, which I've defined above. I give my initial conditions, like I just said, and I give the times that I want to solve it for. And so I can solve it. And remember how long those differential equations were. And watch how fast it's able to solve it. Something that a human couldn't even come close to competing with. It takes a little bit. I think it's like 10, 20 seconds. And so now it's all solved. And now I can get the solutions for the Euler angles, right? And once I have the Euler angles, I get the top of the spinning top as well. And remember that I solve for the top of the spinning top in terms of the Euler angles using this vector here. So I can plot specifically the top of the spinning top. So I get my Euler angles as a function of time by looking at the answer. The answer dot t, answer. The first array will be theta, then theta dot, then phi dot, then psi dot. So it's got all 6 of those variables that I defined. And so I get just theta, phi, and psi using indexing the answer.t. For some reason it comes transposed like that. And then I get the x, y, and z locations of the top of the spinning top as a function of time, and I actually don't need this. Then I can plot theta. So what's the angle? How does it tip, right? You might think I let go of it and it just revolves around and theta doesn't do anything. Well, it turns out that the spinning top is actually kind of going like tipping up and down as it's moving around, right? That's an interesting feature of a spinning top. And finally, I can plot the location of the top of the spinning top, right? If I look at the tip, what's the tip doing as it moves around? And so I can use Plotly for that. I have some Plotly code where I create a layout, I create a figure, and I make just basically a 3D scatter plot. And I have an interactive plot here where the blue is, of course, at the origin, and this traces out the top of the spinning top. And this is beautiful, and this shows what's known as nutation. So as the spinning top revolves around, it's actually kind of doing a little loop-de-loop thing. Remember that the point is fixed, but there's a loop feature here. And shortly, of course, I'll show you the beautiful animation that was created as well. Now, something interesting, right, is we looked at a cylindrically symmetric spinning top. And to some extent, this actually can be solved by hand, and you can predict the motion like that. But the question is, what happens if the mass is unbalanced? For example, what if it's heavier on one side than another? Well, the beauty of the computer is, of course, that I can do that. So here I say the mass of the voxels. It gets heavier as you go up in Z, but also it gets heavier on one side. So the positive x side is actually heavier than the negative x side. It looks like an exponential curve. So one side is a lot heavier than another. So I can resolve this equation and see what happens with the top of the spinning top. For example, what happens if I spin something that's heavier on one side? You get a very interesting solution. And so here's the solution when the spinning top is heavier on one side. And you can see it actually makes an interesting looking pattern here. And it's a little bit hard to see on this plot, and you'll see in the animation in a second, but it's doing sort of a cloud-like motion. And when you watch the animation, you'll kind of think, oh yeah, that is what that happens. Like, you know, there might have been a time in your life when you have spun something that's heavier on one side, and it makes an interesting looking motion. But anyways, let's look at the 3D animation of what's going on here. So all the 3D animation code, of course, was coded up by Amsal at U of T, and I'll let him describe the code briefly right now.
So what I received were kind of the Euler angle histories of the spinning top, and as well as the 3D model STL file. So my programming software of choice is Matlab, because I do most of my research work using Matlab. Initially, what I'm doing is I'm just loading in the structure that actually contains the Euler angles as well as the STL file. After that, we can basically add the 3D model to a Matlab figure and color it however we want. So in this case, I set it with RGB values of 0.5, so that would be gray, because we were going for that Inception spinning top shiny vibe. Then we're using something called homogeneous transforms, which are basically like beefed up versions of rotation matrices. So they're rotation matrices with translations built into them. And they're pretty commonly used in things like robotics and stuff. So what we can do is we can use Matlab to generate these homogeneous transforms by just telling it, hey, I want to translate my 3D model to this location and rotate it by this amount. And it creates a matrix that you can use to multiply into those coordinates to transform them into new coordinates. And then we basically just regenerate the plot at every single time step. So kind of like we're running through a for loop where we'll just be iterating through the different angles with respect to time. So after importing the STL file, we can see that the kind of like the main part of the code, which is lines 47 through 58, is where we're generating those homogeneous transforms through every single column of the Euler angle history. And then we apply that to our untransformed spinning top. And basically through each iteration of the for loop, we're saving how the figure looks into a video file, so that at the end, after when you've gone through the entire for loop, you basically have all the frames saved into a video file that you can play back to any video player.
Anyways, guys, thank you for checking out this video. Please be sure to play around with the code yourself, try new things. What I really encourage is, you know, for example, take the mass of the spinning top. What happens if you do weird things? Maybe if it's heavier in different ways. How does the motion look like of the spinning top when the mass distribution changes? Be sure to like and subscribe this video. Also join the Discord server. That's how I got in contact with Amsal. I said, hey, can you please create a 3D animation, somebody? I don't know how to do this in a very nice way. Amsal reached out to me, and it was basically done within a few hours. So the collaboration that's going on in this Discord is really nice as well. Anyways, I'll see you next time.